Hopefully you saw that I extended the homework for 2.8 to Saturday night. And I don't know if I've said this before. If I haven't, then I apologize for duplicating it. But for the homework, I really hope hope most of you aren't like waiting till the night of or the night before to look at it for the first time. So based on like when I'm getting questions about stuff, I feel like they don't come early. They always come like 10:50 or 11:30 the night before. I do not expect that all of you will be able to do the homework without help. I mean, I think I know I've said that before, but so I think it benefits you to look at it, as early as you can and start like chipping away at it piece by piece. But sometimes they can be pretty long and difficult, so yeah, try not to wait too long on it. But yeah, I'll be, as I said before, if you try to get a hold of me the night before pretty late, it's probably not gonna work. But I do want to say thank you for using the Ed discussion board over the last couple of nights. Thank you. All right, let's get into it. We're still in section 3.2 about inverse functions. Kind of a lot of stuff to get through, but last time we talked about one-to-one functions. So function f is one-to-one, and I think we kind of represent this a few ways, but if you have a pair of x values that are different, then what does that mean about the y values that correspond to them? Maybe I should refresh things here. Is the function I've drawn here one-to-one? Why not? Right, so if I have this like be y0, then I have a pair of x values that both map to that, right? So this is a non-example. But if I have a function that looks like this, that's one-to-one, right? Maybe not. I meant for it to. Yeah, that's a little more convincing. So that's one-to-one. What does that mean? Let me actually write down what I'm looking for. What operator can I put between these two things? Yeah, they must not be equal. So that's probably the most common definition of a one-to-one function. If you have two values in the domain that are different from each other, the function has to map them to different things in the range. But it kind of, as I've shown here, this horizontal line test is kind of the graphical, quick and easy way to think about that as well. Any questions on that? All right, and I think we may have talked about these examples last time, but the function f of x equals x cubed, is that function one-to-one? You okay about that? What is the domain of this function? What's the range? All real as well, right? So one thing we can do here is this. If I have another way to say a function one-to-one is this. Let's see what happens if I have two y values that are equal. I'll call them x and y. So that means x cubed is equal to y cubed. Can I take the cube root of both sides? That'll give me x equals y, right? So that's another way to show that a function is one. You make the y value equal. So if you make the y values equal, and that means that the x is equal as well, that's another way to show one-to-one. And then for those of you who like looking at what the graphs look like, it looks something like this. We're good on x cubed being 1 to 1. What about x squared? So I think we talked about these examples last time. I'll draw the graph just to, for the sake of me posting these later. But you know, if I do the same thing here, f of x equals f of y, that means x squared equals y squared. If x squared equals y squared, does that mean that x equals y? No, give me an example. Yeah, so if x is equal to 2 and y equals -2, then certainly they're different, but squaring them yields the same thing. So x squared is not 1 to 1. So a few more ideas about inverse functions. So if f is a 1 to 1 function with some domain A, some other domain B, or some range B, then this notation here is the inverse of f, which I'm sure you've seen before. And I keep seeing in the textbook to warn people about this. And I'll write it down, even though I don't know if I can remember a time I've ever seen someone interpret this like this. I think in some context, we're used to seeing that -1, which looks like it's an exponent, and we think that's reciprocal. So this is not a thing we're talking about. So that is read f of inverse. What is the domain of f inverse? What did I call that thing? B, right? So the domain of f inverse is B. The range of f inverse is, right? And this is one of the things that, by definition, an inverse function does. Creates those two sets. And I think I did this before, but let's just refresh our memories here. If I know that f of x equals y, then what's a corresponding thing I can say about the inverse? F inverse of y equals x. Which really, that's kind of the same thing as me saying the domain and ranges are flipped. I just took a thing out of the domain and a thing out of the range and showed that relationship. So I'm gonna all but guarantee that you've seen all this stuff before, but it may have been a while. Any questions so far? Let's find the inverse of a function. So you all said that f of x equals x cubed. That was 1 to 1. Would we agree that this thing is 1 to 1 as well? Yeah, all I'm doing is taking that cubic function and translating it upward 2 units. Is this something you remember how to do, is finding the inverse of a function? Walk me through it. Yep. So, and I mean, I think I remember the way I was taught this was just trade x for y without any real explanation as to why you do that. But hopefully by talking about the domain and the range being exchanged, hopefully that makes sense why, you know, I am going to transpose x and y now. All right. And my goal here is to do what? Isolate y. So x minus 2 equals y cubed, and then y equals cube root of x minus 2. And since I started with a function called f, I really want to make this relationship clear that I found this inverse function that corresponds to it. Any questions here? All right. One thing I wanted to show you, open up Desmos. So this is right here in the red, that's f of x equals x cubed plus 2. This right here is the inverse. So if you look at a function and its inverse, the graphs of both of them What do you notice about how they're related to each other? Or maybe what do you remember about how the graphs are related to each other? What? They're flipped over y equals x. Do we know why that is? Right. So I mean, if you're switching the domain and range, really, I'm essentially, if you're thinking about this in terms of graph, become y values and vice versa. Yeah, just to refresh our memories here, that yeah, if you're thinking graphically about a function in its inverse, they're always going to be reflected over that identity y equals x function. So now, can we do this? Can we sketch the graph of this function and its inverse? So before we do that, let's do something else. For this function f, can I figure out what its domain set and range sets are? So this time, hopefully we agree that the domain and range are not going to just be as simple as all real numbers. How can I find the domain of f? Go ahead. Okay. Then remember what the thing is called that's inside the square root? The radicand. Kind of a silly sounding word. So I know I need this thing to be positive, right? Is it really positive, or can I? Yeah, it can be 0. So it just needs to be non-negative. So if I solve this thing, then I will get -1 is greater than or equal to x. It's easier to look at as x is less than or equal to -1. Cool. So the domain for this function is all the x values that are less than -1, less than or equal to -1. Do we know what the range of f is going to be? So here's what I'm hearing: f of x is greater than or equal to 0. Do we agree with that? Think about what happens when you take the square root of numbers that actually give you real values back. They're going to be non-negative. And in this case, like I'm not translating this square root function up or down or anything. So yeah, I agree that the range is going to be all non-negative numbers. Sorry if I messed up your notes with that. So what can I say about the domain and range of f inverse then? What's true about x and what's true about f inverse of x? Think about what inverse functions do. So what's the domain of the inverse going to be? Not greater than or equal to -1. So let's go back to kind of the language we use. Maybe those are words we remember, but maybe not. Maybe the meaning escaped us. What is when you have a function with a domain and range? What does inverting that function do to the domain and range? It exchanges them, right? So if the range of f is values greater than or equal to 0, then the domain of the inverse is values greater than or equal to 0. And if the domain of f is values less than or equal to -1, then the range of the inverse is values less than or equal to -1. Ask me some questions while I try to badly draw some coordinate axes. We okay with how we've defined domain and range?
How did you determine that the range has to be greater than?
More or less function looks like. So compare that function to this one, f of x equals radical x. And if you think back to like transformation of functions, subtracting one is going to move the square root function around horizontally, and multiplying x by -1 is going to reflect your function, your graph, over the y-axis. Those two things are not nearly as important as the fact that they're not going to do anything to change like the verticality of that square root graph. So, oh yeah, go ahead.
I was just saying like negative x, negative, the range is less than equal to 0, but you're saying it's over the line.
Right. So let's try something here. Let's do, what is f of what's something in my domain that I know works? -2. Let's do negative. Yeah, -3. I'm gonna do one more audible, -5. So f of -5 would be -1 minus -5, right? Which would be square root of 4. Should be 2. So even though I have that negative inside the square root, no, we're used to square roots having like a minimum x value. But in this case, because I am taking the x, taking the opposite of it, you know, my domain has a maximum value now. I can only take values -1 or lesser. So I'm actually going to point it out on the graph here. What is f of -1? 0. So that's a good thing to know. And then I can only have values of x that are less than that. And my graph is going to look, oh, didn't want that to be that linear. My graph is going to look something like this, right? Are we okay with this sketch of f here? This point right here is, I'll just list the coordinates of it. -1, 0. So x is equal to -1, y is equal to 0. Question?
Why is it on the
Fantastic. I have to edit this recording later. Okay, you happy now? Okay, thank you. All right, from here, so this is the graph of f. How would I find the graph of the inverse? And we could just find out what the actually invert the function, but let's not. So let's actually just try to do it from the graph. So how would that work? Was that what you were going to say, Cameron? Okay, so yeah, let's to show how they're related, let's put this guy in here. But yeah, I know I have a point -1, 0, right? So what other point do I have? Well, what point exists on the inverse? 0, -1. I believe that is correct. And then what's the graph going to do from there? So we go to the left? To the right, okay. So does that fit with what our domain and range say? It's going to go down to the right, right? Sure. Yeah. We're okay with how that went. If I ask to invert, you can do it. I believe you could, but I wanted to do an example. We're looking through the graph as well. Any questions? All right. So let's talk about derivatives of inverse functions now. So if you have f, which is 1 to 1, and I'm telling you that f inverse of a is equal to b, then we would like to say some information about the derivative of the inverse at a. So a lot of layers of this notation here. Let's draw a picture. So I have a 1 to 1 function. I'm going to think about its graph and its inverse. So I'll call this one f. Try to replicate this. Okay. Good enough representation of the inverse. So what I really want to do with this, I'm trying to figure out something about the derivative. I know that f inverse of a equals b. This is the way I created it before. Doesn't really matter, but I'm going to call the upper one the inverse. So I say I have this point here. I know the coordinates of this point right here are BA, which means that there must be a point on the function f called AB. So let's just come up with a generic name for what this derivative is. And really, we don't know how to take derivatives of inverses. All we know how to do so far is take derivatives of. So let's call this slope right here, this derivative. dy dx. So I'm just going to just draw this right triangle in here to represent the slope. So basically what I'm saying is this. The derivative at a is equal to dy dx. So if we think about the way that inverse functions treat their domains and their ranges, and I know this derivative for the function f is dy dx at that point, can I say anything about derivatives, the slope on this other line over here? Here's going to be exactly the same. So this vertical part of this triangle is dy, right? So would you believe that makes the horizontal part of this triangle dy? That's true. This is the part that, so this is called the inverse function theorem. That's the kind of the hard thing to.
Well, what do you want the next means? Here, dy, right? One thing or like do so this vertical is the other way to say, what happens if you take a vertical line and reflect it across? And similarly for the horizontal dx. Yeah, so that's some other smoking is next to it. All the values. That change if you were dy. A piece of paper and fold it across that slant, and I hope that'll convince you. So now that we have this dy dx reflected over that y equals x line, now we'd like to say something about the inverse, the derivative of the inverse at a. So it's equal to dx dy, right? But it's equal to that where x equals b. Don't really like dealing in things like dx dy, so I would like to represent it like this. 1 over dy dx, where x is equal to b. Not leaving myself enough room for this. Leave the punchline. It's just saying like the. So do you want to be that vertical line that when you think of slope, you think of right over run, right? So in this case, that line just figure out, trying to figure out what's the next. Yeah. Well, because so this straight line right here. So right now, I'm gonna say something like this. Because you mean why is this input right here a?
Yeah.
Oh, okay. So we're going to take a function f, we're going to invert it,
we're going to differentiate that function a, or sorry, differentiate that function f inverse and put a into it, right? But if I'm thinking about the point f inverse of a, so let me spell this out here. Do we agree that this is true? So our end goal here is to get this, and this will be more obvious when I put the next slide up, but we're trying to say something about the derivative of the inverse function, but we would like to use the input values. So let me pause and go to the next slide where the actual punchline is. So basically this right here is called the inverse function theorem. So it's a way to talk about the derivative of an inverse by also instead think of it as a derivative of it. Sorry. How can I relate the derivative of an inverse function? This is just another way to look at these ideas. So it's not obvious from the way this is written, but what this buys us in a practical sense is instead of having to take the inverse of a function and then differentiate it, I can just take my basic function by my original function f, take the inverse, take the derivative, and handle them separately. And the first bullet there that I kind of blew past says that basically if a function is one-to-one and continuous, then its inverse is also continuous. All right, should we look at an example? This thing here, f of x equals 2x plus cosine x. I want to find. Let's remind ourselves here. What is? How do I re-express n inverse prime of 1? So I believe this is. So now let's just break it down into pieces. Can we find f inverse of 1? We agree that f inverse of 1 is going to come from where this is true. So if f inverse of 1 equals x, then f of x equals 1. Hopefully you agree I'm allowed to say that. And I have this, 2x plus cosine x equals 1. The very last step I had? So I'm trying to find something out about what happens at f of inverse of 1, right? So I just gave it a name. I'm calling that unknown x. I really want to find what that x value is that makes the function equal to 1. So this is not a function that can be solved by algebra. When I say it can't be solved, I mean it cannot be done. So I will offer this, and hopefully you believe me. What is the cosine of 0?
And 2 times 0 is 0, so we're good. So what is F inverse of 1? Yep. So I can continue by finding F prime of 0. Now, how do I find F prime of 0? What's the derivative of that original function? 2 minus sine of x. So F prime of 0 is equal to 2 minus sine of 0, which is 2. So my final derivative is going to be 1/2. Question?
How did you get? Where's that come?
Yeah.
Minus sine of 0.
I want to point out here is, let's say that you didn't know this theorem and you want to just try to find the inverse of 2x plus cosine x. Hopefully you take my word for it, but that can't be done. So, think about your typical way we try to invert functions. I have x equals 2y plus cosine y. You're not going to isolate y. So trying to find an inverse and then take a derivative is not going to work. Granted, it's kind of a complicated theorem, a little hard to get your head around, but sometimes it's absolutely necessary. Instead of trying to take the derivative of the inverse, that inverse function theorem allows us to use F inverse and F prime. So its inverse and its derivative separately. Because trying to take the derivative of the inverse directly is going to be impossible. We renamed. Oh, yeah. So in trying to find F inverse of 1, basically we had to solve this original equation. Set it equal to 1 to solve. Any other questions about this one? Hey. The 1/2. So let's talk about logarithmic functions. So basically what a logarithm is, and the reason they were invented was before then we did not have an inverse to the idea of exponentiation. So raising something to a power did not have an inverse that we could use. So that's what these do. So, has anyone in here dealt with logarithms before? Okay, that's good. So these two ideas here say the same thing. The one base in of x, y, and a to the power y. Couple of key identities here. So if we think about what the logarithm
Right. I have to raise A2. And that's. For that, the next.
Now about that bottom one, a to the power of log base a of x. I'm highlighting why we do that. Because it's not really canceling per se, but before too long, you mean you're kind of you're gonna learn that that's a shortcut you can take. But just to unpack the second one a little bit more, let's just rewrite this out. Log base a of x is equal to y, right? So couldn't I just say that a to the y equals something? And what if we already said that a to the power of y is equal to? Right? What? That's basically what I was trying to illustrate over here. So I just took this exponent and brought it off to the side over here. And I just gave it the same name that I gave it above. So if I can rewrite that exponent as y, and I have a to the y here, I've already defined this in general terms as a to the y equals x. These identities are really useful for simplifying logs, which is something that we're going to have to do going forward. So we've already looked at these, so I'm just going to fill them in. But the reason that I had us look at these the other day is because to make these logarithm laws a little easier to see where they came from. But if you think of a logarithm as the inverse of exponentiation, if I have two like bases and different exponents multiplied together, I just add the exponents, right? So if I take the inverse there, so the base here is a. I'm taking the log base a of xy. That's going to be equivalent to this, log base a of x plus the log base b of y. Not base b, sorry. Log base a of y. The log base a of x minus log base a of y. And finally, if you kind of look at the power to a power rule, you're just multiplying the powers together, right? So if I have the log base a of some variable x raised to some power r, that's the same as log base a of x multiplied by r. Are these things you've seen before? Long time ago? Now, not so long ago. Any questions? I can. So I want to evaluate this thing. So by the end of this, I'll be able to just like give back a number. But based on the laws we just looked at, how can we start simplifying this? Okay, so log base 2 of 80 over 5, which is equal to the log base 2 of 16. Do I know what log base 2 of 16 is? I'm gonna vote for 4. Do we see why that is? I'm gonna guess that not everyone does, which is fine for where we are. That's exactly it. So I believe that all of us, me included, are just more comfortable in dealing with exponents. So one thing you can always do, you can always rewrite a log in the form of an exponent. So this right here, I can translate this to 2 to the x equals 16, which hopefully, if you don't recognize that x equals 4, you can count up a little bit and you'll find it. Any questions there? I'm gonna go ahead and stop there. So I only got a minute left, and this next thing will get a little more complicated. Can. And I have some graded stuff if you want to stick around. Nicholas, we got here. Oh yeah. So 2x squared minus 4xy. Y squared equals. You found x. Now you know that it just has to be y for that to make sense. And you can solve this quadratic.
That was for the question back. John Ross, I haven't heard it over there. Finally. So. Yeah. Yeah. So remember, basically your college. All these processes. And then you can divide it. There's some that. I want. Perfect. You can text my detail size. Use that. He needs the power. Well, I don't remember. My first nickel are used to read. Square root of 23. Yeah.